I'm Jacob Cooper, and this is our Physics 2211 Lab 1 presentation on constant velocity. A little bit of an introduction. Our purpose here to observe the motion of an object moving at the same speed without changing direction, which is just constant velocity. Our object was a Jeep Wrangler. I took a video. We put into a tracker program that gave us some data along with the observational model. We used some of the data that it gave us and we put it into GlowScript, which allows us to run VPython programs, which gave us a computational model, which we'll see in a little bit, and we're also going to compare the two. And really here we're just trying to demonstrate some of the principles of Newton's second law. What is Newton's second law, or the momentum principle? And that is that the definition: net force is equal to the change in momentum over the change in time. We have our equation here. Using this, we could derive some more. Being final velocity is equal to initial velocity plus net force over mass times change in time. Final position equals initial position plus average velocity times change in time. And you'll see those being used here in a little bit. Here's our video tracker. Basic. We have some data over here. Our mass, 2,358.68 kilograms. Our initial time, final time, initial position, final position. We plug this to our average velocity formula, which is displacement over change in time. We got 8.57 seconds, meters per second. Sorry. Going on to the next slide. We have our GlowScript program. A couple key points here. We start seeing some of the data from, we just looked at, being used here in our code. So, I have our 0.2 meters for our position, our initial position, initial velocity. We have our 8.57 meters per second. Here we see, our time being in between our, start and finish time, which is, pretty intuitive. Another key point here, we have our vector, our net force vector being set to 0. And that's just because, with constant velocity, our net force is going to be 0. There's no acceleration. And then down here on lines 58 and 60, we have our final velocity and final position equations being implemented, which is the ones we just went over. So we're kind of seeing all this stuff come together here. Another key point to look at is that really the mass doesn't even matter in this case, because our net force is 0. So we're dividing 0 by number, we're just gonna get 0. So the mass doesn't really matter. Next we have our model, comparing our two models. In the orange we have computational, the blue we have our experimental, and there's some discrepancies there, but we're about to discuss those. And so here's a few follow-up questions on that. What if our positive x's and negative x's were interchanged? And to answer that, pretty simple, is that we would just have a negative slope for our velocity, meaning our object would be moving in the opposite direction. A good way to look at this is if we flipped this over the x-axis. It's a good way to look at it. Next question: is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observe? Really, in this case, just observing our object in motion, it's impossible to say how, nearly impossible to say how many forces act upon our object to give 0 net force. But we start looking at, some potential errors. We look at our discrepancies here. We could conclude that, there may have been some forces acting upon our object, maybe friction, maybe air resistance, or, maybe there was just some errors in our tracker software, maybe in our video. And so I'm going to conclude on that. And thanks so much.